Hey guys, maybe this is a good point to also get into or get prepared for the next session. Thanks, Alexander, for chairing the first session. So I'll very gradually take over. However, now welcome to the second session of the day, and we are very happy to have Itsuko Ito. I hope I did not completely mispronounce that here to give a presentation. Thank you for sharing your screen. That's amazing. And this is really nice to hear because a second ago in the previous session, we had Hiroshi Shinaoka give a presentation on the sparse modeling approach in a condensed matter kind of surrounding. And now we will see how Itsuko brings this to a very interesting application in QCD, which is the shear viscosity, which I think many of the people who are in the audience now have actually worked on in the past. So I think it's really exciting to now see this new model here, and also the application of the Wilson flow smearing here and how this worked out for you guys. Really exciting. So I think we should just start. I know it's just 2 minutes between past 11, but I think you can go ahead. Thank you.
Okay, thank you very much. So first of all, I'd like to thank organizer for inviting me this interesting workshop. Thank you very much. And today I would like to introduce my recent work, collaboration with Yuki Nagai. He is also condensed matter theorist based on this paper. And in this paper, we investigate the QCD shear viscosity using the sparse modeling approach and from the smeared correlation function, which is calculated by the gradient flow method in the lattice QCD calculation. And in this paper, still give a first step to obtain the shear viscosity. So here, I'd like to introduce the methodology of the gradient flow method and the sparse modeling method. Okay. So let me start briefly. What is QCD shear viscosity? And as you know, around the critical temperature between the hadronic quark-gluon plasma phase transition, small eta over S shear viscosity to thermal entropy ratio has been suggested by the several experiments. But in the theoretical side, it is hard to precisely determine the value of eta over S. Actually, the thermal entropy is somehow precisely determined by the lattice QCD calculation. But the problem is how to find the precise data of eta in the lattice QCD calculation. And this shear viscosity is given by the spectral function rho omega, and the shear viscosity is proportional to the first differential coefficient around the frequency omega equal to 0. And this spectral function is defined from the Euclidean correlation function of renormalized spatial energy momentum tensor. So T12 renormalized energy momentum tensor. So in the lattice QCD calculation, we firstly measure the disk quantity using the generated configuration, and we obtain the C tau, and we estimate the spectral function using the second equal. And here, K integration kernel is given by the hyperbolic cosine function in the finite temperature QCD. And this kernel is independent of Monte Carlo data. It is important in the sparse modeling analysis. Okay, and however, the theoretical side, we have at least 3 essential difficulties to obtain the shear viscosity. First one is a somehow theoretical issue. So how to define the renormalized energy momentum tensor on the lattice? Because as you know, energy momentum tensor is a generator of general covariance, but such a covariance is explicitly broken on the lattice. And the second one is how to improve the path signal to noise ratio of correlation function of energy momentum tensor. Actually, energy momentum tensor has the same quantum number with QCD vacuum, so signal is quite noisy. So we need the huge amount of the configuration. And the third one is the main topics of this workshop, how to estimate the spectral function from the limited number of data of the correlation function. In particular, in the finite temperature QCD, we have a few number of data of the correlation function, actually order 10. So series inverse problem appear. And in our answer is as for the first and second difficulty, gradient flow method looks promising. Actually, the gradient flow method to define the energy momentum tensor is proposed by us 7 years ago, a collaboration with Asakawa-san, Hatsuda-san, Kitazawa-san, and Suzuki-san. And as for the third difficulty, sparse modeling method seems very powerful. And actually, previous speaker, Shinaoka-san, and his collaborator, condensed matter theorist, proposed this method. So we apply this sparse modeling method to the QCD. That is QCD. Okay, so let me briefly give a review of the what is the gradient flow method. So the renormalized energy momentum tensor in the gradient flow method is given by this equation. So this is a renormalized energy momentum tensor is given by the lattice-Clover operator U mu nu and the trace part of the Clover operator E. And here T is denotes the gradient flow time. And in this X denotes the four-dimensional space-time coordinate. And here is tau denotes the imaginary time. And according to the Suzuki-san's paper, he gave some coefficient of alpha U and alpha E using the following discussion. So using the Suzuki-san's coefficient, so we can obtain the renormalized energy momentum tensor from the lattice observable. And the Suzuki-san's basic idea is the following. So general quantum field theory suffer from the UV divergence. So we have to regulate the theory to find the finite physical quantity. Energy momentum tensor is also a physical quantity. And we have the famous perturbative regularization. And if we use dimensional regularization, then general covariance is preserved. And we perform the Yang-Mills gradient flow in this continuum theory side. And on the other hand, we also have the other regularization method, so-called lattice non-perturbative regularization. And we also know the corresponding technique with of the lattice Yang-Mills gradient flow, which is called Yang-Mills gradient Wilson flow on the lattice. After taking a continuum limit at the finite Wilson flow time, so both quantity is UV finite. So the UV finiteness has been proven by the Lucia and Wise in this paper 2011. So so then the both side as a physical quantity are UV finite. So we can find the matching condition in the perturbative region, and then we can obtain the this operator equation to define the renormalized energy momentum tensor. This is a basic idea to solve the how to define the renormalized energy momentum tensor. And the second difficulty is improvement of the signal to noise ratio. And as for this difficulty, again, gradient flow method is very useful because gradient flow is somehow continuous stout smearing or continuous block spin transformation. So it reduces statistical fluctuation. And actually link operator around this region at the flow time t are smeared and UV fluctuation suppressed and the signal become clear. But to use this gradient flow method, we have to take care of the length of the flow time. So there is a fiduciary window of flow time. So the fiduciary window is given by the theoretically as this equation inequality. Actually, flow time should be longer than the lattice spacing to reduce the lattice discretization effect. And to avoid the over-smearing come from the finiteness of the lattice extent. So the flow time should be shorter than the half of lattice extent. And the actual data of the one-point function of energy momentum tensor, we find the data shows a somehow plateau region in this fiduciary window. That is a highlight of our previous paper. And now we would like to apply this gradient flow method to measure the two-point function of energy momentum tensor, this one. So first of all, let me show you the improvement of the signal to noise ratio. So in this plot, we generate the only 2000 to 5000 configuration. So if we do not perform the gradient flow, the non-flooded correlation function is quite noisy. And you see some data are missing because some non-smeared data take a negative value because of large fluctuation. However, once we perform the gradient flow, so the smeared correlation function correctly takes a positive value with a small statistical error. Okay, and here is the flow time dependence of the smeared correlation function. So in this plot, a different color denotes the different flow time. So green one is the longest flow time, and the black one is a small flow time. And first of all, you see that in long flow time, so the data has a smaller error in whole tau region. And in the long tau region, the data, several flow time overlapped each other. However, in the short tau region, there is a discrepancy depending on the flow time. And that discrepancy comes from the over-smearing effect. So let me explain this part. So now we would like to measure the correlation between the white circle operator and red circle operator, and at the tau and tau equal to 0. And so at the finite gradient flow time, the white operator smeared around this region. And if we take the long flow time, then the smeared region overlapped to the red, another operator, red one. So here we would like to find the correlation between white and red operator, but if the smeared region overlapped the other operator, then we cannot find the correct correlation between them. So we would like to eliminate such data suffer from the over-smearing from the analysis to estimate the spectral function. So now sparse modeling method come. So so far we see the gradient flow method looks very promising for the first and second difficulty. However, the gradient flow method makes the third difficulty harder. So estimation of the spectral function. So let me explain this. So essential difficulty, third difficulty, come from the smallness of the number of data point of correlation function. So originally we have the disintegration equation, and we discretize it to the set of linear equations. And now vector C has a n tau component, and vector rho has a n omega component. And according to the linear algebra, so if n tau is smaller than n omega, then the several possible solutions are allowed it. So we cannot find the unique solution. So, and as I explained it, the flooded correlation function in short tau region are deformed by the oversmearing. So if we eliminate such oversmeared data, then situation getting worse. So we need some powerful tool to find the spectral function from the very limited data of the smeared correlation function. And until now, there are several estimation methods of the spectral function from the non-smeared correlation function has been proposed. So first one is fitting data using some ansatz, and or find the likely function based on Bayesian statistics, for instance, maximal entropy method. And the sparse modeling method is advantage of the sparse modeling method is the following. So first of all, we perform the singular value decomposition of this kernel matrix. And it is, as I explained it, it is independent of the Monte Carlo data. So the property of the singular value is independent of the Monte Carlo data. And we, as Shinaoka-san explained it, we transform the vector C and rho into the Ri basis using the unitary matrix U and V. Then the rank of rho prime becomes the same with C prime and tau. And actually, the C, this is the actual data of the C prime and rho prime in the IIR basis in our analysis. So original optimization problem, the cost function is given by this equation, original correlation function C vector and kernel and rho vector. So we would like to find the rho to minimize this cost function. But here K is non-diagonal. So error bar of the correlation C and rho is not linearly related to each other. But in the IR basis, the cost function is given by the C prime minus S and rho prime. And here S is a diagonal matrix. So the each component C prime and rho prime are linearly related. So the statistical error, we expect the statistical error indicates the satisfied this equation, and actually our data also almost satisfies this expected relationship. And the third one is most non-trivial part of the sparse modeling method, as Shinaoka-san explained it. We add the L1 regularization term to the optimization problem to be consistent with the reduction of the mode or vector. So we introduce a L1 regularization term into the optimization problem. So the cost function is given by this part and previous part, and we add the L1 term, and here lambda is a Lagrange multiplier. And we would like to find the rho prime, minimize this sum of these two terms. And as Shinaoka-san explained it, so only the first term, so there are several candidates for the rho prime. in the low prime plane. But if we add the L1 constraint, it pick up this open circle point where the L2 component is 0. So we can essentially drop the L2 low 2 component in our analysis. So this L1 regularization term favors a solution with a small number of components. And in my understanding, so in this situation, the row 2 takes a positive value, both positive and negative value. So such a property gives an instability of the solution. So, and we pin down the row 2 equal to 0 in this scheme. And this is a very intuitive, good test to explain the role of L1 term. Actually, this is given by Shinaoka-san's paper. So if we take a large value of lambda, L1 regularization term, as a result of sparse modeling analysis, red curve becomes featureless. So it corresponds to the underfitting. So where the L1 regularization term is too strong and the number of components of low prime vector is too reduced. On the other hand, if we take the small number of lambda, then the obtained result of the spectral function has artificial spikes. So it corresponds to the overfitting, where the L1 regularization term is too weak. Then the vector low prime has a redundancy. And so in the sparse modeling analysis, we tune the value of lambda and find the good spectral function. And the algorithm is very complicated, so you can find the numerical code. I didn't know that Shinaoka-san also opened the code, so we also opened our numerical code on the archive page, and I think it may be the same standard cost function. So this is our cost function. We introduced the spectral sum rule and L1 regularization term and non-negativity of the spectral function. And in our actual analysis of our paper, we drop the sum rule, take the mu equal to 0, since we eliminated some data of correlation function. So I think this that procedure breaks the sum rule. And now optimization problem has several constraints. And to solve such an optimization problem with under some constraint, there is somehow recent algorithm, so-called ADMM algorithm. So we can solve this kind of the problem. Okay. And this is again the Shinaoka-san's test result. So yeah, actually, let me focus on the this plot. So they investigated the stability against the Gaussian noise in the correlation function. And yeah, in this plot, that plot fascinated me. So because the sparse modeling analysis gives a very stable spectral function, in particular around the omega equal to 0. So let me remind the shear viscosity is proportional to the first differential coefficient of rho around the omega equal to 0. So it looks promising to find the shear viscosity using the sparse modeling method. That is the starting point of my work. Okay, so now I'd like to briefly introduce simulation result for the quenched QCD. So this is a simulation setup. We utilize the Wilson bracket gauge action, and we generated the lattice size is 16 for cubic times 16. And the coupling constant is a fixed this value. And the number of configuration is only 2000. So this is a quite small number of configuration in comparison with Nakamura Sakai's paper 2005. Nakamura-san generated the 800,000 configuration. Actually, I heard from Nakamura-san, he accumulated data for more than 5 years. So it's great. And recently, Borjani and his collaborator generated the 6 million configuration for one parameter to obtain the viscosity in the quantity QCD. And actually, they take the continuum limit. So in total, they generated much more configuration. So, and this parameter, lattice parameter, corresponds to this temperature. And to find the eta over S, the value of thermal entropy is given by this value from our first paper. Okay. And this is a result of the spectral function obtained by the sparse modeling method from the smeared correlation function. So this is a small flow time, and actually T over A square is 0.5, 1.0, 1.5, and this is a long flow time data. So first of all, let me consider the integration of the spectral function. It corresponds to the sum of degree of freedom of the system. So according as a function of gradient flow time, so the sum of degree of freedom gets smaller in the long flow time. So, and let me remind that gradient flow can be interpreted as a renormalization group flow, and the renormalization group flow decreases the degree of freedom of the system. And in particular, we focus on the high frequency mode here, here, and here, and here. So we find the high frequency mode gradually suppressed by the gradient flow. So these results support the intuitive property of gradient flow as a renormalization group flow. So this is a somewhat surprise. So the sparse modeling analysis reproduces such a property of the gradient flow method. And the statistical error in the long flow time is small as expected. And this is a comparison plot of the input correlation function, black data, and output correlation function, red data, which is constructed by the obtained spectral function in the previous slide. So we see the output correlation function almost reproduce the input data. So the sparse modeling analysis works very well. And this is a current status on the shear viscosity in the quenched QCD. So in our analysis, we have not taken the continuum limit, and flow time goes to zero limit yet. So it may not be fair to compare our data with other work. But anyway, our data is here, green one. And in this plot, some data take a continuum limit, and the other one is have not yet. But anyway, message is here. Our statistic data, only 2000 configuration, can give a result of the viscosity by combination of the gradient flow and a sparse modeling method. And actually, in our paper, we investigate several systematic error or stability of the spectral function using the sparse modeling method. So, but it looks under controlled. So, this is my conclusion. So, towards the precise determination of the viscosity, So combination of the gradient flow and sparse modeling method looks very promising in both theoretical and technical meaning. And so but the sparse modeling method itself is a general framework to estimate the spectral function from correlation function. So it will be a powerful tool for the various subjects in the lattice QCD calculation. Okay, that's all. Thank you.
Super. Thank you very much. That was very interesting talk. Any questions right now? One hand is up by Andre. I think you were first. Please go.
Yeah, actually, my comment is that your equation, which how to say, connect tensor correlation function to the spectral function rho from omega, the kernel is completely identical to that which connects the current correlation function to the optical conductivity in condensed matter. And your viscosity is absolutely the same as mobility, which enters the condensed matter. So in principle, we are doing absolutely the same equation for different reasons, but mathematically, these two equations are absolutely identical. So maybe it has sense to try once to do it by different method, because as for my experience, when you send something to journal made by different methods, it hardly improves the possibility to be accepted to this journal if you do something by several methods. So that's all I wanted to say. Thank you.
Oh, okay, thank you.
Okay, Harvey, you had a question?
Yeah, so on these results that you had in the quenched theory,
yeah,
I was wondering if you can see the shape of the spectral function, maybe one slide previous, yeah, around omega equals 0. So, you know, do you see, if you divide the spectral function by omega, you know, does it have a positive or negative curvature at omega equals 0?
Yeah, good question. So actually,
in other words, is there some kind of a peak there or not?
Yes, okay. So this is actually my paper. So actually, yeah, this is that. And actually, this rho tilde is a rho divided by the hyperbolic tangent omega. So
okay, that's just as good. Yeah.
And yeah, actually the curvature is depend on the actually the flow gradient flow time. Yeah. So yeah, I don't know what, but
it depends on the flow time. Okay.
Yeah, but finally we will take the t goes to 0 limit. So I think the positive curvature will be correct in the t goes to 0 limit. Yeah, in the small flow time, it has a positive curvature. Yeah.
Okay. Yeah.
Thank you.
The thing that was on my mind is, you know, so the question is, if they are quasi-particles in the medium, then you expect to see this kind of transport peak, not just in the energy momentum tensor correlator, but essentially in any, in the correlation function of any operator that has the same quantum numbers. Unless you tune it to not couple to the quasi-particles, but if you just pick, you know, some operator, it will have some coupling to this quasi-particle, and so in the width of this peak, if there is such a peak, then is somehow the inverse lifetime of this quasi-particle, and so is something kind of universal. That's why it's particularly interesting, this feature.
Okay, I see.
And then, of course, there are theories which do not have quasi-particles at all. So then it's not even, the curvature is positive in ADCFT type calculations, right? The curvature is just positive, so that there's simply no sign of a quasi-particle.
Okay, thank you very much.
Thank you.
That's very interesting. Thanks for that comment and discussion. Are there any other questions? Otherwise, I suggest we go to the second talk of the session.
Okay.
I don't see any
Thank
right
you
now.
very
So
much.
thank you, Itsuko, one more time. That was really great. Thanks.
Thank you.
And we go to Shoji Hashimoto. We are also very happy to have you here this time. And you will be talking, shifting gears a little bit. So we are not going to be talking about sparse modeling anymore, but very interesting work about getting inclusive processes, inclusive information out of smeared spectral functions. And I don't want to give away too much. So Shoji, please take it away. Thank you.
Okay, thank you. Good afternoon, everyone. I'm discussing on a slightly different perspective. I am not going to try to solve the impulse problem, but still want to find the physics applications of the spectral function. So let me start with the general introduction that everyone shares. I mean, everyone shares the same problem, starting from the lattice data, whether we can reconstruct the spectral function. That is the famous ill-posed problem, and everyone here is struggling about what is the best way to do that. And I think everyone also knows that where the problem comes from. That is basically because in this Laplace transformation, lots of information is lost when you compute, when you obtain the correlators from the spectral function because of the structure of the Laplace transform. So in other words, the matrix we are thinking about, it has a very many small eigenvalues that could be 10 to the minus 5 or 10 to the minus 10. So some of them are extremely small. So the corresponding modes are lost when you do the Laplace transform. So the inverse is extremely difficult because the information is no longer there when you have the correlators. That is my interpretation. So my question is what we can do in this situation. So I'm more like a pragmatist. So I do not try to solve the problem fully, but I've tried to find what we can do in this situation. So the key is the smearing. And I'm not the first to advertise the way of this thinking. Some years ago, 40-something years ago, Poggio, Quinn, Weinberg introduced the smearing of the spectral function. In this particular case, the R ratio for the E plus E minus to QQ bar. And by introducing the smearing function, initially the spectral function has lots of sharp peaks and bumps and many interesting structures. But using perturbation theory, then analyzing those complicated structure is extremely hard, and that is a completely non-perturbative question. So what they did was to introduce the smearing with some widths. They found that they can analyze the experimental data using the perturbation theory. So this is still the experimental data transformed in some way, I mean the smearing. And so it is not as ambitious as one would try to analyze the original spectral function, but you can still analyze the experimental data using your theoretical tool. So it's still an interesting thing to look at. So I would try to do the same thing using the lattice data and think about what we can do if we are interested in the smeared spectral function. So this is the example. Let's consider the 2-point function, the vacuum polarization function, for instance, and it's a bread and butter to compute the correlation function on the lattice, and that is written in a simpler way. That is the matrix. Matrix element form of the correlation function. Here, from the vacuum, you apply the electromagnetic current and to produce all possible states. And depending on the energy of the state, that state decays according to the Euclidean time with the transfer matrix and get back to the vacuum once again with the electromagnetic current. So what we are calculating on the lattice is this sort of matrix element, J, transfer matrix J. On the other hand, the structure function has a different form. Here, again, using the same the matrix element form, you can represent it as the matrix element of the delta function with delta omega minus Hamiltonian, because you are interested in the component or the number of states having a given energy omega. So this is a very difficult problem starting from the lattice data to obtain the spectral function. On the other hand, what I would advertise is to consider some sort of smearing. I do not specify the functional form right now, but let's consider the smearing with some function S of delta. So by applying this smearing, the delta function in the one line above can be written in a different way, S delta, omega, and Hamiltonian. The omega prime is integrated over while doing the smearing, and that variable can be replaced using replaced by the Hamiltonian. So this is the matrix form of the smearing function. So what you are interested in, what I am trying to compute is the matrix element of the smearing function S delta, omega, and Hamiltonian. So the question is whether this operator S delta can be written using the transfer matrix with arbitrary time. That is the question I'll try to address. Okay. That approximation can be established the most conveniently using the Chebyshev approximation. Here, the S delta, the smearing function, is given in terms of the Chebyshev polynomials with an argument of exponential minus h hat the transform matrix of one time step. And you probably know that what the Chebyshev polynomial is, and that is this is one example of that, and these are the Chebyshev polynomials, and the high orders of polynomials are constructed using the recursive form. And this is a famous story of the approximation theory, that any function in a given range can be nicely approximated using the Chebyshev polynomial. And actually, you can obtain the best approximation. Here, the best means that the maximal deviation is minimal. That is the meaning of the best approximation here. So whatever the function is, my smearing function could be any sort of the function. But whatever the function is, there is a mathematically defined way to write down the best approximation. That is the Chebyshev approximation. And the coefficient Cj can be easily obtained once you specify the original function. So that is independent of the lattice data or whatever. That once you give the function using the well-defined integral, you can obtain the coefficient. So this is an example. Here I take the sort of the Bright-Wigner type, the function, the kind of a smearing function, and see how well one can approximate this function using the Chebyshev polynomial. And that depends on the range of the smearing. And there are three plots here. From left to right, the smearing range is narrower to wider. So looking at the rightmost plot, the true function, Bright-Wigner function, is given by the solid curve, and the three approximations are written with a particular order of the polynomials, 10, 15, and 20. And you can see that if you have 15 or maybe 20 polynomials, then you can nicely follow the exact solution, true solution. So the approximation is really nice in this scale. But going to the narrower and narrower smearing, the approximation gets harder. And you can easily imagine that if you take the limit of the smearing width going to 0, the approximation gets extremely hard. That is the same problem of the ill-posed inverse problem. So I'm not that ambitious enough, so I would be satisfied with a relatively wide smearing, so that we can approximate precisely using the Chebyshev approximation and obtain the final result. And the coefficients of the Chebyshev expansion is like this. Here, the coefficient, absolute value of the coefficient is written in terms of the polynomial order. If you simply look at the blue, that is the widest, in this particular example, widest the smearing width, the coefficient going to exponentially suppressed for the higher orders. And we know that the Chebyshev matrix element of the Chebyshev operator is always bounded by 1. Absolute value is bounded by 1. So 1 times the coefficient, that is 10 to the minus something, is the contribution of the next order. So your smearing range is sufficiently wide. We have actually controlled approximation of the whole thing. On the other hand, going to the narrower smearing, you can see that the coefficient doesn't decrease much. That means that the remaining error is still large. So the problem of the ill-posed inverse problem manifests itself in the decrease of the coefficient there. Okay. So we did it. Here is an example using the charmonium spectrum, and on the right I specified some certain width of the smearing, and then we obtained the smeared spectrum to be almost independent of the polynomial orders. So we are confident about the error of this computation. But going to the narrower and the narrower smearing width, smearing range, the approximation gets more difficult, and you probably need higher order terms. By the way, the order of polynomials needed to compute directly related to the time range on the lattice, because here the Tj is just a polynomial of x, and for the order of j, the highest polynomial order is x to the jth power, and there the x actually means exponential minus Hamiltonian, so that means the highest order is exponential minus j times Hamiltonian. So with larger j, you need the larger time separations of the correlators. Okay.
Can I just ask what the quantum numbers were of this charmonium?
In this particular case, I think it's pseudoscalar, but you can do the same thing for the vector.
Thank you.
Mm-hmm. Okay, and we can also try to look at what is the individual contribution of the ground state and the first excited state, because we can analyze and we can fit those lowest lying state. So and we can see how wide my smearing is. So actually these are the ground state and the first excited states. So if I take my smearing range safe enough, wide enough to estimate precisely, we somehow lose the structure of the ground state and the first excited state. But in order to get to some resolution of the ground state and the first excited state, we probably need much narrower smearing range. And in that region, the approximation gets worse, and you probably need longer and longer time separations. That is difficult because of the noise problem. That is the situation. So there is no free lunch, but anyway, that is the situation. So what one can do under this situation? The previous example is interesting because you can analyze the spectral function or the R ratio in the E plus E minus 2 QQ bar in a certain way. But there are other examples, there are other applications of the method. That is my favorite B-meson decay. Here we think about the B-meson semi-leptonic decay. Here the B quark decays to the charm quark and produces the final state hadrons. That could be the ground state D meson or D star mesons. It could be D pi pi or and so on. There are a bunch of power of those states. And the people typically use the exclusive mode, the ground state contribution to extract the CKM matrix element VCB. But you can do the same thing considering the inclusive rate, because the experimentalists can actually measure the inclusive rate. Here, the inclusive means you measure all possible final state and sum up all of them to extract the BCB. So how to analyze such a process is there is a standard way to introduce the structure function. Here, the differential decay rate is given by the product of the leptonic tensor and the hadronic tensor, and the hadronic tensor has another name of the structure function, and that is written there, W mu nu, and this is it describes the B meson decays to all possible final state X, and X comes back to the B meson with the dagger of the operator, and so it looks pretty much like the spectral function in the previous example. The only difference is that here the initial state is not the vacuum, but the B meson. That is the only difference. And if we replace the initial state by B, the same thing applies. And if we are able to obtain the matrix element of the delta function, we can reproduce the whole spectrum of the structure function, and then you can finally obtain the differential decay rate. But what we actually want to compute is not the spectrum. Of course, if we can compute the spectrum, full spectrum, that is very nice. But what the experimenters measure is not the precise spectrum, but more like the total decay rate. And that is given in this way. The total decay width is integral of that spectral function over the energy of the final hadronic state and the spatial momentum of the final hadronic states. So if you integrate over those, you can obtain the total decay rate. That is the formula. So, and here K means the kinematical factor that is determined by the leptonic tensor. So that is a fully known function. So what you can do is to put this K inside of the matrix element to obtain, I'm sorry, it's not given here, I'm sorry. You put this K inside of the matrix element, and then you can replace the omega by the Hamiltonian. That is exactly the same story as before. So I look at this, the kinematical factor K, to be the smearing function. Then the whole thing is the whole story is the same. The kinematical factor is the smearing function, and this is a particular form of the kinematical factor that we have to introduce. Here, you can trust me that there is a kinematical factor, but the important thing is that there is an Heaviside theta function that drops off to 0 because of the kinematical constraint. Your final hadronic state has to be has an energy lower than certain value. So there is a Heaviside function here. So the function is something like this, going up and suddenly drop to 0. So this is not easy to implement because of the sudden sudden move of the function. So I would introduce the sort of the smearing function. Here, to be specific, I introduced the sigmoid type smearing function with some width. So this is not exactly the sharp singular function, but is a sort of a smeared function. So again, if I introduce a large enough smearing, the approximation is easier, and going to the smaller smearing width, approximation gets harder. So, and in the end, we have to take the limit of sigma or the width going to 0, that is shown on the right top plot, and we can do the extrapolation to sigma to 0. So, and we use the actual lattice data we obtained on the parameters such and such, and there are choices of the operators to insert because of the weak interaction. The current J is actually the vector minus axial vector, V minus A structure, and the mu and nu could be any combinations. And after all, you have to sum over all possible combinations of those. And some of them are shown here, and the correlators with the barrier varying the time separations between the two currents are shown there. So that shows nice exponential fall off. And starting from here, I apply the same the trick I just explained to obtain the final results, such as this one. Here, this is the differential decay rate divided by the momentum absolute value. So if you multiply the momentum and integrate over the momentum, you finally obtain the inclusive decay rate. And this is the particular example for B to charm decay, but the charm Cork mass is physical, but the B Cork mass is unphysically light. So it doesn't correspond, unfortunately, it doesn't correspond to the physical situation. But in this study, we look at this artificial setup and obtain this result. And by the way, the band is represent the contributions of the ground state, B to D or B to D star. So, and the data points are showing the inclusive rate. So it looks like the inclusive rate is actually dominated by the ground state contribution. And that is sort of expected because the initial B quark is not that heavy compared to the physical situation. So there is not so much room between the B quark, initial B quark and the final charm quark. So the most likely the ground state contribution dominates the whole thing, but the computation itself is done in a way that the inclusive computation is possible. Okay, so I'm summarizing. Inclusive processes can be considered a smeared spectrum, and that can be computed using lattice QCD. And the important thing is that here the error can be well under control, because the higher order the Chebyshev matrix element is always bounded by plus and minus 1, and we know the coefficient. So what happens when I add more and more terms, and what would be the error corresponding to that can be computed or estimated reliably. That is probably an important thing here. And the finite volume errors I can address if there is any question. And there are applications, semileptonic B decays, maybe D meson decays. I'm also interested in the lepton nucleon scattering, and the people consider the pattern distribution function and so on, but that cannot be used for the low energy scattering. But in this method, we can analyze whatever the energy is, so that you can access to the low energy scattering region that is relevant to the most recent neutrino experiment. So and inelastic scattering relevant to the neutrino experiment. So such an application would also be interesting. Okay, that's it. Thank you very much.
Thank you, Shodri. That was very, very interesting. Thank you very much. Any questions from the audience right now? Please raise your hands. Question by Nazario.
Hi, Shoji.
Hello.
You know that I know exactly what you're doing. So I'd like you to comment on the fact that the correlator is not used exactly as it comes out from the situation, from the simulation, because the coefficients of the e to the minus jh is growing doubly exponential. And so this object may introduce very large errors. So in your method, there is a pre-processing of the correlator, right?
Not really. I'm not sure what you mean.
I mean, you fit the correlator in terms of the correlator itself in terms of Chebyshev polynomials.
Yes. Maybe, yeah.
This is an important point from the point of view methodology. It's not a criticism. It's just that I want to highlight this important step.
Yes. That is something like technical but very important point. I mentioned that the Chebyshev matrix element is bounded by plus or minus 1. But if you look at the original construction of the Chebyshev polynomial given in this way, and the individual terms of x to the some power, if you literally use the lattice data in this way, that constraint can be easily violated, especially for high orders. At the lowest orders, the precision is good enough and that kind of problem doesn't happen. But going to the higher orders, you have the large coefficient times small correlators. And that is summed up with the plus or minus signs. So that can be very noisy, and within the noise, that coefficient can be much larger than, Chebyshev matrix element can be much larger than plus or minus 1. Then the whole approximation procedure is broken down. So we have to be careful that constraint is satisfied. I think Nazario is talking about that problem.
Exactly. And so in your analysis, you fit the correlator in order to impose this constraint, right?
Yes.
Okay, Max?
Yeah, I also had a question on this slide, I think. So what we can see from this slide quite clearly is that this is a linear method that forms some linear combination of the Laplace kernel time slice by time slice. And of course, we know there's a very broad family of ways of doing this. There's the original Backus-Gilbert ideas with various minimizing functionals.
Yes.
So my question is, you have some favorite set of coefficients here, and then you can check the reconstructed smearing function. If someone derives an alternative set of coefficients, even if you don't know where they come from, do you agree that you could just check to see if they're better? And it's just possible that you can get a better set by not restricting yourself to the Chebyshev polynomials?
Yeah. The better or not, I can't tell right now, but I'm happy with any approximation.
Yeah, so the point I want to make is, of course, you can check, given the coefficients, you can check the quality of the smearing function. So,
yes.
So I don't see a reason to restrict oneself to these Chebyshevs.
Well, yeah, that is a theoretical simplicity. To me, the Chebyshev matrix element is always less than 1, and the coefficient is well defined and easy to estimate the truncation errors. But you are right. Any other method would be fine.
Okay. I don't see any other questions right now. So thank you, Shoji, for that talk one more time. That was really, really great. Everybody, please stay online because we seamlessly go into a discussion session, which will be led by Max on the things that we have heard about the broad picture kind of overview. And Max, are you ready? Then we can...
Yeah, I have 3 slides. So I don't want to over restrict this. I really would encourage people to bring up whatever topics are on their minds. But maybe I'll flash these slides just to further stimulate the discussion before we jump in. I can also keep track of the chat. Yeah. Okay, so I think there's such a consensus here about how ubiquitous this problem is and how important it is to solve. So I don't want to dwell on that, but it's of course fun to reiterate and reestablish that this really matters in a huge variety of sciences, from geology and atmospheric sciences to various image processing, and of course to engineering and physics. One thing I was asked to focus on was observables, and I now realize that my expertise is only a small part of the full workshop here. I really enjoyed these other condensed matter contexts. So here I can really only comment on observables in the context of particle physics. And if you ask the question, what observables can we get from spectral functions? I think the short answer is somehow everything. And what we focused on in this workshop, including in the last talk, are inclusive hadronic rates, as well as scattering, decay, and transition amplitudes. So any sort of hadronic state in and out together with some external currents. And what we've also seen in previous and in upcoming talks are thermal quantities, properties of thermal QFT, as well as a broad family of light cone distribution functions. So with that in mind, here's some of the questions that I thought might be fun to stimulate the discussion. I actually have a second slide, but let's focus on this first. So I'll just read them out quickly and then we can see if any of them spark interest. So one thing that has come up in my mind in many discussions is what is the most useful way that we can really quantify the severity of an inverse problem? And I think based on exactly what question we ask, there's sort of a continuum of how severe the problem is. So I think it's interesting to understand how do we quantify the severity or otherwise characterize the problem. I think some experts might know a lot more about this than I do. Another question to ponder is, of course, how we're treating systematic uncertainties. In the context of either lattice field theory or other numerical methods, I think it's important to understand which sources of systematic uncertainty are most important and do we need to understand them better. And really this falls into 2 camps. First, there's systematic uncertainties on the input data we need to understand, and then there's those induced by the reconstruction. A third question is, we've heard all these different ideas of how to solve the same problem. And it feels sometimes to me that I don't know how to fit them into a broader landscape. It seems like these should all be connected in some massive sort of flow chart. So I would like to hear comments on how do we organize the landscape of reconstruction methods and how do we meaningfully compare them? For example, how do we really systematically identify which methods have which strengths and weaknesses? And here are some of the buzzwords that people like to advertise for their methods. And then finally, I wanted to touch on the issue we saw this morning. Is it always necessary to regularize the inverse problem in some way? And are we sometimes regularizing without realizing it? Or sometimes the regulator hidden in some way? And so I'll leave it there for now. Maybe let's jump in with this first question if anyone has a comment. Is there some knowledge out there about systematic ways of defining the severity of the inverse problem? Yeah, go ahead, Alexander.
So, one of the things that has been reoccurring, sorry for the noise in the background, is we are usually dealing with linear transformations, and they might look innocuous like a cosine transform, where at the first sight for me, for example, the severity of the inverse problem might not at all be obvious. And it seems this as a topic that that repeatedly came up was the smallness of the eigenvalues, because that somehow indicates the amplification of noise-related issues in the reconstruction. So if we could somehow rewrite or state the severity in the sense of largest eigenvalue versus smallest eigenvalue kind of a criterion. That at least seems to be a criterion that would apply to many of the problems we have seen so far.
Yeah, I mean, that seems like a really natural choice, just some condition number, right? So maybe an interesting follow-up there is, can I come up with two inverse problems that have the same condition number, but actually have different severities in practice? That there's some, subleading issues that even if the eigenvalue hierarchy is the same between the largest and the smallest, maybe the details of the eigenvalues in the middle can matter as well.
But this is intimately related to with the structure of the error that one has, because I mean, if you look at the singular value decomposition of the linear problem, this is totally independent from the input data. If in one way you can solve this by using arbitrary precision arithmetic, as we suggested, that would not be a problem. I mean, the true problem is the noise in the error data once you have a very singular eigenvalue in the game. So the two things, in fact, are strictly related. And I would like to be pointed to a way to quantify this on the side of the error.
Yeah, exactly. So I can't help but my knowledge here is really almost entirely on the side of Backus-Gilbert-like ideas. And there it just feels incredibly natural that you have this ill-conditioned matrix. So that's one aspect of the inverse problem. You have the covariance matrix of your data that also somehow measures that issue. So somehow forming a linear combination of them seems a very natural way to see that balance. A related question there is, for example, if I use Backus-Gilbert as a metric of how severe the inverse problem is, do other reconstruction methods agree with that metric? Do I see if it's difficult according to Backus-Gilbert that also MEM struggles?
So then I think it has to do with the amount of relevant prior information that you can provide, because you might be able to render some of those small eigenvalues completely irrelevant if you had enough prior information to restrict, say, the large UV range of your problem. And by that, you would be reducing the severity of the problem as you add additional information that is not yet present in the data. So that would add another quantity to the covariance matrix that somehow then describes the relevance of the individual modes for the final solution, I guess.
Yeah, I mean, that naturally also connects to this question down here as far as sort of criteria for judging. So I think we've mentioned the issue a few times. How important is it to be completely driven by sort of only the Monte Carlo data, say, that you get from the calculation?
On this perspective, Max, sorry if I interrupt again, I fully agree with Alexander, and I want to justify and to motivate my question to Shoji Tol, because in fact I wanted him to highlight this nice feature that he introduced on a standard Chebyshev reconstruction, because what he's doing on the side of the correlator is to impose an exact constraint that comes from theory. So to use some prior in order to filter the data and make the problem more handful, more tractable. From this point of view, I consider this step the most important step of Shoji work on the reconstruction side, barring phenomenology applications.
Yeah, I agree. I mean, somehow one has a sense that it's very nice if you can really document these aspects when you describe the reconstruction method, which I think everyone has been doing, but it's somehow nice to imagine this sort of bulleted list of, first of all, whether or not it's linear, what kinds of external inputs are coming into it, just to really have that in mind when comparing different methods, that these two differ because this one has an extra external theoretical input, and therefore it should do better.
When viewed from a Bayesian perspective, this kind of so I think this ties in with your second bullet point, Max, with the uncertainty quantification. That, in some sense, I would like to think about each point of that spectral function as given by a distribution, not and this was also a point of, I think, Andre's contribution this morning, that this is, we are not looking for the best spectral function anymore, I would say, but we are looking for a distribution of values of the spectral function at a certain point, and then the shape and the width of that distribution can help us or can tell us about the reliability and the systematic effects that are in there. The difficulty that I see here is that we then have to really formulate everything in terms of probability distributions, which might not be straightforward if I have some rules and things like this that somehow introduce very intricate correlations between different points of my spectral function. But in the end, so what I would love to be able to produce from a reconstruction method would be a set of distributions for each value of the spectral function that then contain both the effects of the systematic or prior information input that I chose and the uncertainty that is somehow present in the data, and those somehow again folded together would then give me the overall error budget or systematic plus statistic uncertainty budget.
Yeah, I mean, I think this is a very recurring topic in lattice calculations, and I'm sure in other numerical methods. Even when reconstruction and inverse problems aren't involved, there's a bit of a discussion between building a histogram or building an ensemble to represent systematic uncertainty. There are groups that make heavy use of this. There are groups that are concerned that this is maybe too aggressive. And I don't know, the point that comes to my mind is what Harvey already said this morning, that how can we really understand that we have a meaningful distribution and that our choices in building the distribution at the start aren't biasing the final result. And I think this example with the rectangles that we saw this morning, I mean, somehow that's a very clear recipe that you use random numbers, but of course you still have to choose the range of random numbers that you allow, how many rectangles you allow, what positions you allow them to form. You have to make the choice to only look in the space of positive definite functions. So I think it's just really good to catalog those inputs and understand, is that a rigorous distribution in the same way of a traditional Monte Carlo with a proper accept reject step? I think it's hard to answer these questions.
Perhaps one question towards the second point as well, which says systematic uncertainties on the input. So this is a question actually. So the role of the correlations between the data, because most of our data is actually generated from some Markov chain or something. So our theoretical data is somehow correlated in most cases, sometimes more, sometimes less. But this should also impact the reconstruction in some way, like in precisely in the way that you just mentioned and what Harvey mentioned this morning, because you're somehow biasing the choice even implicitly through the data that you have fed in. The solution of it is kind of given by the data you fed, of course. And I'm wondering, is there any understanding how, like in these methods, if I think of MEM or if I think of what Andre showed this morning, I don't see a clear handle of how you could understand that, while in something like the Backus-Gilbert, you kind of have this covariance matrix so that it enters explicitly and you have this handle in your hand. Also in the sparse modeling, how does the correlations of the data enter in this situation? Especially if it's not just diagonal, if it's like there's actual correlations in the data.
Yeah, absolutely.
I also want to add, there is not only the correlation between the input data. Of course, with different analytic continuation, we choose the transformation of the covariance matrix. It gives a slightly different result. But what is important is the correlation of the spectral function itself. So for example, if you look at a different, as we call it, independent solution, which we have, then these different independent solutions has some fluctuation. So you can estimate the error bars. But these error bars is not the true, are not the true error bars. So whenever you just take one point and try to push it to another height, so as I did, I just push one point to higher position or lower position. In this case, I have the transformation of the neighboring parts of the spectrum. So it means that if you want to be always within the error bars of the input data, even your spectral data are correlated. So if you just try to touch one point, then another points also move in your spectrum.
Yeah, no, it's a really important point. And yeah, I mean, there's a lot one can say. Of course, another point that comes to mind is we often just struggle to have reliable estimates of our covariance matrices, even on the input lattice data. And so there's a question, there's some uncertainty in that matrix itself. And just because that may be an acceptable determination for, say, getting the ground state mass, it could be problematic for these more ambitious observables. It's just hard to know. Yeah, go ahead, Harvey.
Yeah, sometimes you can wonder even, so why do we even attempt, to attack this inverse problem? So I think there are cases where, so if you think of this R, the famous R ratio, right, in the vector vacuum correlator, it doesn't make too much sense because it's known so well experimentally, right? So if you want to somehow compare the theory with experiment, you would just transform that spectral function from experiment and compare it to the lattice data as it is. Of course, you can work in different bases. You don't have to work in Euclidean time by Euclidean time and so on. But then, of course, there are the more interesting cases where there's some things that are known about the spectral function, but not everything. And of course, to do the spectral integral, you have to know the whole spectral function, right? So those are the cases where there has to be some middle ground where you meet, right, between theory and experiment, or between the knowledge you have from spectral function and from Euclidean correlation functions. And so that's where these methods come in, I think. So it's always worth thinking about whether there are some clever observables, right, which are still accessible from experiment, but where you have a reduced uncertainty from this inverse problem, or even no uncertainty. So there's obviously there's some moments of the lattice data which you can just determine without any uncertainty in this inverse problem aspect. And the question is whether you can make sufficiently good contact with experiment. So I think to learn something, you have to find usually a middle ground like this.
Yeah, I think it's really an incredibly important point. So yeah, somehow one should first make a list of every piece of physical information you can squeeze out of the correlators without solving an inverse problem, and make this as absolutely exhaustive as possible. And then only then ask the question, by attacking in some form of inverse problem, can I really add meaningful information? Or is it already covered in these more attainable observables? In fact, maybe I'll jump to the next slide. This is the remaining set of questions. And the first one, I think, is exactly your point, Harvey. Can we identify, and these are going to be highly observable and field-dependent opportunities to partially circumvent the inverse problem? And what I think is also very remarkable, sometimes this can really be seen as kind of a journey around the complex plane of some amplitude or correlator. So this is something I've also discussed with Shoji, and one can see in the R ratio in other contexts. You typically have some subthreshold region where you can really integrate with, say, a growing exponential, and that gives the analytic continuation as you want it in that subthreshold region. You then have a region where you're on top of a branch cut, where you have a very severe inverse problem. But then you can also define something, up the imaginary axis, which is somehow in between. So it's nice to sort of have this continuum and to see what one can do with that.
Right. The experimenters have a handle to look at the spectrum by themselves. So they can analyze the data in a different way with different weight function, for instance. And if that is more tractable theoretically, there's no reason not to consider such quantities. I fully agree.
Yeah, and of course, G-2 has just been an incredible effort for us to learn everything there's to learn about how to play with these observables, these various weight functions. This technology is probably valuable to apply elsewhere. Yeah, go ahead, Alexander.
Yeah.
So this is a very interesting point also at finite temperature. So for example, there's the question of transport coefficients. And this is one of the hardest of those problems, I would say, because we are trying to get access to the low omega region of our spectral functions there. And in the context of quarkonium physics, there's work where one tries to reformulate, exactly as you say, for specific physics cases, whether one can actually somehow find Euclidean observables that directly encode the relevant information so that you can circumvent the inverse problem altogether. And indeed, this has been, there's efforts, for example, on heavy quark diffusion and such to realize this, but this is then really depends very specifically on the physical process at hand. And somehow one might be lucky or not that it works, but I agree that this is definitely something that one should explore before throwing in gazillions of core hours, maybe or at least have it as a strategy running concurrently to see can we maybe go at this from different directions. Yes.
Yeah, absolutely. Harvey, were you about to say something as well?
Yeah, maybe just to add to this point on you have to choose your inverse problem in a sense. So exactly in these decays, inclusive decays, one has the question of which variable is kept fixed when one writes this dispersion relation, and by which one wants to reconstruct the spectral function. So and typically there one has a choice with a fixed spatial momentum, and in relativistic theories one can also do it at a fixed space-like virtuality in some cases, and it makes a difference, I mean, which one you do. And so one should think what is more profitable, where do you learn more?
Yeah, absolutely.
So, and certainly there are applications where having the virtuality fixed is more interesting, because that, for example, corresponds to virtuality 0, would correspond to some real photons, and that is in some sense closer to the way the experimentalists are working. So just a more useful variable set.
Yeah.
But it depends on every case, basically.
Exactly. I mean, I remember we also thought about this in the context of our work for inclusive D decays and the hadronic tensor. And the kind of funny observation there is, of course, the lattice calculation has a reduced symmetry relative to the infinite volume continuum that you want to describe. And what that means is you have kinematic choices on the lattice that would all be redundant in the infinite volume continuum. So, the final thing is just a function of some Lorentz invariance, but the lattice thing, it really cares about the specific values of P vector. And so you can make a list of lattice kinematics that all correspond to the same infinite volume continuum point. And then you can play a lot with, which ones are fuzzy and which ones are sharp to get the best determination.
just to add a comment also on this point, I mean, this is extremely relevant and of course requires that we start organizing this kind of workshop also with experimentalists, because we might want, for example, to agree on which kind of smearing, not really the shape, but windowing that on the analysis of experimental data have to be done on given observables. Because, I mean, this is likely not to happen for observables that have a solid, or if you want, have a theoretical estimate, because experimentalists tend to continue to do what they do once they can compare with something. But if we are talking about the charm exclusive or inclusive decays in which you don't have essentially nothing to compare with, and on the other hand, there are plenty of measurements at LHCb or other facilities, and you try to say to an experimenter, look, if you don't do nothing different, you will never get something to compare with. But if you smear your data in this window with this function, you will have something pretty solid to compare with. Yeah. Then we might win. So we should try to agree on which kind of smearing to do, and to convince experimentalists on the observables where nothing else is available to do this kind of analysis.
Yeah, I think it's a great point. I mean, you can imagine even stronger, say, constraints on CKM matrix elements coming from really identifying the perfect thing to compare. Maybe I can make one miscellaneous comment. Mostly in the talks we've seen so far, when we have smearing, it's smearing in some physical coordinate, some physical energy, for example, which is often important for the intuition and also tells us when things are going to be very tough. If we know the right answer has a very sharp peak, then we know the smearing will be a major distortion. It turns out for scattering amplitudes, where you're really getting the amplitude rather than some rate, in that case, the smearing is in an unphysical coordinate and really one of the particles being off shell. So I think there's a separate challenge there, that we have less intuition about the smeared coordinate because it's something unphysical. Okay, so just for completeness, you can see the questions here. I don't know if you need to read them, but I think it's very interesting to understand, do we agree to what extent we're completely estimating the systematic uncertainties? And you see I've broken this into categories. And so this is already my bias, that I think it's for smeared spectral functions reconstructed using linear methods that we have the highest confidence that we can understand the systematic uncertainties. And as you move down here, at least I have less confidence. So with nonlinear methods, I would pose the question, if it's harder to have a full reliable systematic budget, and then when we're really targeting the underlying unsmeared spectral function, I would argue, or I would ask if we agree that it's even more challenging.
So one way how to implement these, the finite resolution in the nonlinear methods would be by an appropriate choice of basis. And in the linear methods, this basis is usually suggested through the shape of the kernel itself, for example. While for the nonlinear methods, somehow the two, depending, since the nonlinearity often refers to some choice of prior information, but nevertheless, we are still allowed to add the information on resolution back into the approach. And for example, one could think of ways like using Fourier modes as basis functions for the spectral functions, because that would be a basis where you have a clearly defined smallest and highest resolution limit that you can choose according to the problem at hand. So in that sense, I think endowing the standard Bayesian methods with such kind of a resolution criterion would be a straightforward way.
Look, Alexander, I agree. I will briefly mention in tomorrow talks, for example, a very preliminary exploration that we are doing with the machine learning technique. In that case, for example, you have a nonlinear method, And once you understand that smearing is important, you train your network by teaching it to recognize the smeared spectral density instead of the unsmeared one. For theoretical reason, because this might be not defined, or because just it might be simpler to get the result and to alleviate the complexity of the problem. So the point is recognizing that this step is essential, and then to implement it in whatever method, from my point of view.
Good. There is a question in the chat. I think just about what do we mean by smearing? Yeah. So we're really imagining this idea where you have G of tau is equal to the Laplace transform of rho of omega.
Yeah.
And what we're saying is you don't directly get out rho of omega, but you get out a smeared version. So rho of omega convoluted with some resolution function. So it's not a smearing of G of tau, but it's saying that the thing we extract at the end of the day is going to be smeared out.
Okay. So, but Ito-san, right? Thought, yeah, actually in the slide of Ito-san somehow without gradient flow, something like that.
Yes.
So I think that, I mean, there's a lot of ways to also smear the input data to smear the underlying correlator, but to some extent it's logically separate. So you could play around with smearing the input, which I do think is very interesting. And then you stick that into the inverse problem. So the specific choice on how you smear the correlator can define the inverse problem you're solving. But then a second step is whether you target a smeared spectral function or how you do that.
Okay, so there are two different things. So, but if I understand correctly, it's Ito-san's talk. So smearing introduced some errors or systematic errors near tau equals 0 and beta, right? Is it correct? So you throw away some data near tau equals 0 and beta. Or if you only fit data near, somewhere in between.
Yeah, I don't know. I can't connect my understanding to that perspective on it.
So I think that wasn't that related to the fact that one had a finite smearing radius, and Ito-san wanted to make sure that if you have a correlation function that has a certain separation between the sink and source operator, that you make sure that the separation is larger than the smearing radius, so not to have an overlap, what I think you called over smeared regime. So I think that's why there was some points neglected, because there the systematics of the smearing somehow might be less under control, if I represent that correctly, Ito-san.
There's really two different things here. So one is the smearing of the input data, which is you're actively changing this the underlying spectral function through some method. In this case, gradient flow, but you know theoretically that will not affect the region of the spectral function that you're interested in. So particularly in the gradient flow, this affects the UV. But you're interested in your IR quantity, so you're okay with smearing. But this does show up in the correlation function. If you've smeared very far, then you do see effects in the correlator itself. However, the spectral reconstruction method you do, it still has got the same goal. The goal is to reconstruct that data as and minimize whatever your spectral function gives in respect to the distance to that data. Once you did the forward transform, so you have a spectral function, you transform it, compare it to the data, and you minimize that distance. But when you do this other thing, what we also call smearing, which Max just mentioned, it's a little bit different, because what you're trying to get is actually the true spectral function convoluted with some function that somehow encapsulates your ignorance of the exact spectrum underlying it. And and this is where this Backus-Gilbert comes in, why we talk about it so much, because that gives it to you. And this is special because the resolution function, this convolution, if you then do the integral transform to it and calculate the correlation function that this smeared spectral function would give, then it is actually not the same as the data. So you're not doing anymore this minimization that we typically do, but instead the goal is, can we understand this resolution function? Because when this resolution function becomes narrow, infinitely narrow, and the width goes to 0, then the smeared spectral function will be exactly the one of the data, and we will get exact congruence of the two. So it's a little bit different, but these are two different things. So you can yeah, just as a quick background.
Yeah.
Yes, question or a comment? Go ahead.
Well, a comment concerning the smearing or use of gradient flow for operators. So if you do that at finite smearing or finite flow time, then you have no longer guarantee of positivity of the spectral function. That sometimes is forgotten or ignored. So there one has to be very careful. And then usually what you have to do is you have to do the continuum limit and then the flow time to 0 limit, and only then you can do the spectral reconstruction. And only then the analytic continuation is well defined. So at finite flow time, the analytic continuation is not well defined and problematic.
Yeah.
Of course, this is a problem because we have to do the continuum limit, which needs in the lattice calculation. Requires large lattices and so on. I liked your results very much.
Actually,
this morning. But of course, this should be the final goal to do all these.
And actually, our strategy to taking a continuum limit and flow time goes to 0 limit, we will calculate the eta over s at the finite flow time, and we will take a flow time goes to 0 limit. This is our strategy. And I think it is, we cannot deal with, we will not deal with the spectral function itself. We will find the eta over s at the flow time. Yeah, I think. It is a better
the
strategy.
Spectral reconstruction at finite flow time is not, or is problematic, I would say. One has to take care that in the large omega part, the spectral function might not be positive.
Yeah.
So if you leave out data at in the UV, so leave out some of the first data points which are flow dependent, then this might be okay, but still there are, of course, theoretical issues with that.
Okay, thank you.
Very good. Okay, I also hadn't followed all the different contexts of smearing, but I think it's been made clear now. Also, thanks to Anthony for setting up the different meanings. Okay, so this question here is a little bit provocative. Some might say unnecessarily provocative, but it is somehow clear that because this problem is being attacked from all these different communities, that to some extent we do rediscover each other's methods, or we develop methods that we then discover are also in older papers. And I don't think there's anything wrong with that a priori. People always sort this out in the end. I think really it just emphasizes the importance of these kinds of workshops, that by bringing together people from as different communities as possible, we can really encourage the crosstalk here and take advantage of ideas that have been established elsewhere. And then this question I just wanted to highlight because I think Alexander's point was very nice, but actually go ahead first, Harvey, please.
Yeah, I just wanted to say that also it depends a bit so which method you should choose and so on. It depends a bit on what you want to do with the result. So there may be cases where it's not a big problem if you get the wrong answer in some sense. You know, for example, suppose you were searching for interesting materials which have a certain feature in the spectral function. You could simulate those potential materials with the Euclidean simulations, and you do the inverse problem, and then you see, okay, this one is a candidate for having an interesting spectral function. Then I'm going to do an experiment on this. If you got it wrong, it's you waste a bit of time maybe, but it's not a big deal. Whereas often case here in the QCD context, we we want to determine some important parameter, CKM matrix element, or so it is a problem if we get it wrong in a sense. Yeah. So this is also something one has to bear in mind, I think, especially with these machine learning methods. You know, it's also if you're doing an internet search and you know the first 5 hits are nonsense that don't interest you. It's not so bad, right? You just click on the 6th link. It's a different situation, right? That's what I wanted to say.
Yeah, that's a great point. And even in the context of machine learning within physics or machine learning within lattice QCD, there are these 2 camps. So if you're using machine learning to propose gauge fields, then the worst thing that can happen is it's very inefficient. And in the accept reject step, everything gets rejected, but it doesn't create any uncontrolled bias. Whereas when you're using it for these methods, as you say, Harvey, it can have consequences that are hard to detect.
I guess that's the point, isn't it? I was just going to elaborate on maybe on Harvey's point that in his nice example, when you can do the experiment directly to check, you of course immediately know whether you were right or not, but very often we can't. And so understanding the systematics becomes really very important then, because we don't know, it's the only way we have to actually understand whether we got the right answer or not in QCD, for example.
Yeah. So when we're giving our introductory slides and we say, look at how great these methods work in all these other fields, we have to be aware there might be important differences to what we're trying to do in our own field.
Yeah, exactly.
So I'm a bit biased, obviously, from the Bayesian side, but one thing that I've tried in the way how I try to somehow approach learning about everyone else's methods was to ask the question, can I reformulate it in a Bayesian fashion? And for example, the Tikhonov approach that was mentioned several times today. For example, if from a Bayesian perspective, I look at the Tikhonov, this to me is a Bayesian method with a Gaussian prior probability and a 0 default model in some sense. And so if I can make such kind of a reformulation, then immediately it becomes clear to me in the context of my community or the Bayesian community, that are the pitfalls I need to be aware of if I have such kind of a prior probability. And one of the things that I haven't been able to do so far, but this workshop has already given me some inputs to this, to better understand, for example, the Backus-Gilbert and the linear methods more clearly in terms of a Bayesian picture. And that I hope would give us another viewpoint, which hopefully not only would help the Bayesianists better appreciate what you guys are doing with the linear methods, but might also help us in the cataloging of systematics, for example.
Yeah, certainly. I think that really goes to this sort of question about organizing the landscape method. Yeah. That one can see them as different cases in this bigger picture.
I would emphasize what the Nazario said once again. With the linear method, what you called, we can add extra constraints in the analysis that I mentioned several times, that the matrix element of the Chebyshev polynomial is bounded by plus or minus 1. That is a direct consequence of the transfer matrix eigenvalues is between 0 and 1. And that constraint is actually very useful to further constrain the final result. And there are many of those constraints at every order of the polynomial, which means that there are constraints that the number and the same as the number of the correlator time slices. So that kind of extra information should probably be imposed in other methods. I think that is not given there, and probably this is a sort of the reinventing the wheel or something like that. But you should probably think about adding such an extra information that will help you.
Yeah, very good. Yeah, go ahead. Johnny Wow, did you have a question or a comment?
Yes, yeah, it's kind of slightly brainstorming, but it's, so there's, I'm not sure, can you show your previous slides, question for discussion? I'm just wonder, yeah, so it's, I mean, it kind of goes to the how do we organize landscape, but it's a question which I think has been raised already and is missing from these questions. And this is just when you organize a landscape of reconstruction methods, what are the strengths and weaknesses of the different methods? So I think we're in a state where we do need different methods for different problems.
Yeah.
And my own bias. So I know the Asmed spectral functions certainly have a strength in their control of systematics, but if I'm looking for trying to extract, now this is a hard problem which we're trying to make progress on, but extract the width of a narrow resonance peak. I know that guys in doing scattering things have other approaches from this, and maybe we can learn from what's happening in the study of scattering at zero temperature and see, can that be applied at high temperature and circumvent the inverse problem that way? But now you guys are getting into the inverse problem as well, so that's but just from the face of it, using a Asmed spectral function won't work for trying to get the width of a narrow peak.
Yeah, absolutely.
Then you might want to ask the next problem, which is, okay, what's the phenomenological? Okay, we're interested in it from a purely theoretical point of view, but then what's the phenomenological importance of it, or what does it teach us in terms of what happens, say, in a heavy ion collision, where suddenly you have to convolute that with some say hydrodynamic simulation on top of it to get at experimental data. So we get to the problem in some cases the experimental data are clean and you can do direct check of your output with experimental data. In other case, it's a very complicated process to connect it to experiment as well.
Yeah.
So that's another complication that you will have. So this is just thoughts that I'm throwing out, but it's certainly another question of sort of probably some Bayesian methods might have an advantage that at least they pretend to be able to identify narrow peaks, and maybe the sparse reconstruction method can be sort of, it's got similarities anyway.
Yeah, I mean, two thoughts come to mind. So first, I think you summarized the point really nicely about the linear methods. I mean, the strength and the weakness of the linear methods is often you're over smeared. And so to speak, you don't get out the information you want, but you understand exactly the information that comes out. And so it depends how much you prioritize that even though it's not the physics I want, I understand exactly its meaning, which of course has some value. And then as far as methods that can produce more narrow peaks, there I think the important point is, what's the mode for failure? Because it could be that the numerical data that comes out of my calculation just can't constrain the width of this peak. And so I certainly need my method to tell me that information's not there, or else I just cook up a number that's totally generated by the method.
Yes, yeah, and that's probably connects to how do we quantify systematic uncertainties, because
yeah, exactly right.
It should be probably encoded in systematic uncertainty of the method.
Yeah, yeah, that's incredibly important.
Maybe on the finite temperature side, if I may, one of the reasons for using the smeared spectral function approaches, I guess, is motivated by the fact that somehow on a finite grid in a zero temperature calculation, any type of resonance will be very sparsely populated with peaks, or so to say, the structure that in the infinite volume limit will correspond to the true envelope of that peak is only very sparsely populated. And at finite temperature, one can surely think of similar questions. On the other hand, it seems that we might be a bit more lucky there, that the peaks are actually bunching quite happily. So if one looks at, for example, free spectral functions on the lattice, I mean, once you go to volumes of, say, 128 cube, there's virtually no more difference, maybe I'm exaggerating a bit, between the infinite volume shape of these spectral functions and the finite volume result. And so I might be trying to sell a bit of an optimism for extracting the widths of at least some finite temperature structures, because we simply might have the number, so to say, from the way how the spatial momenta can come together in these finite temperature correlation functions and spectral functions, that it might be possible to make sense out of a actual width, which I understand is very different and much harder at zero temperature.
Yeah, certainly at zero temperature, you can think through the finite volume states, and sometimes you can just see, okay, in this box size, there's only one state in the resonant region.
Yep.
So this can't possibly know anything about the width, because there's
yes.
only one state contributing, which is a way that the finite volume tells you you don't have enough. I mean, what that means is if you get precise enough to reconstruct the individual peaks, then your volume uncertainties would just dominate over your statistical uncertainties. So you somehow need a regime where the statistical uncertainty dominates the volume effect, but the volume is big enough that multiple states contribute in the resonant region.
You know, saying this might indicate that we are actually even on the worse end, because what you're then gaining from is that you have access to that one peak in that region of interest, and by isolating its change with volume, you actually gain information about the infinite volume limit, if I understand this correctly.
Yeah. I mean, that is, so to speak, the standard zero temperature.
Exactly. And since we have some bunching going on, we usually cannot extract the individual delta peaks, but we might still be off from the infinite volume limits. So indeed, we are sitting there in a conundrum, maybe. Okay.
Yeah, I agree.
But this is Nazario's point from yesterday. The volumes might not be as huge as depending, of course, on the system. But he said, like, look, you'd have a number of volumes, and if the volume is large enough, you're de facto doing an infinite volume calculation.
Yeah, I mean, to me, the guiding principle is always that, in some sense, the statistical uncertainty dominates over the systematic volume effect.
Yeah, and to that point, like, yeah, Nazario yesterday already pointed out, finite temperature might be easier because it has this more narrow population density of the states. And we do know some examples. Heavy quark diffusion was one. Like, it also depends on what you're trying to reconstruct. If your spectral function is pretty much flat, then even a very broad smearing kernel will reproduce the correct spectral function. So it really depends on the features, I think, in many ways.
Yeah. Very nice. Well, maybe we should wrap it up. We're kind of at the hour, I guess.
Yes.
Thanks a lot, everyone. I'll leave the progress question for people to ponder on their own.
Yeah, thanks, Max. That was a really great discussion session. Thank you for leading this. Really great slides. Thanks. This is the end of today's day for the workshop. See you all tomorrow in the afternoon. So tomorrow we start at 1, not in the morning. But yeah, so I really enjoyed. See you tomorrow.